Jai Hind. Today our topic of discussion is subgroups. It is one topic of 4th unit of discrete mathematics. So what we are going to cover today is introduction to groups, when an algebraic structure is called a group, what are subgroups, cosets, and some important properties and theorems on subgroups. So the references are Discrete Mathematics and its Structure from Rosen and Discrete Mathematics from Leipzig. So these are the references that I have taken, and now let me take the topic. So I am starting with groups. What is a group? When we are given an algebraic structure such that G is a non-empty set with a binary operation, let me call it star, then G with this binary operation star, that is G star, forms a group if the following axioms hold. So what are the axioms? These following, or we can call when these particular properties are holding. First one is associative law. If we take any element from the set G, the elements are A, B, C. So these three elements when we take from G and the associative law hold, then we say associative property is true. What is associative law? For all ABC belonging to G, ABC will be equal to A into BC. So when I am saying here into, it means I am referring to the given operation. My operation is star. So this is a simplified notation to represent our operation performed. So if I expand it using the operation, it will be actually A star B star C is equal to A star B star C. It means whether I perform operation on AB first and the resultant value with C, or I performed operation with B and C first and then the result with A. So both the cases we will get the same value. Identity. If identity property holds, what does it mean? It means in the group G, there exists an element E. So in group itself, we are having an element G such that A into E is equal to E into A is equal to A. So what does it mean? A star E is equal to E star A is equal to A for every A belonging to G. This is our simplified notation. By writing this, actually we mean A star E. This is the simplified notation for A star E. So the point we want to say is, we are having an element such that when we do operation of any element of the group with that particular element, and the first element is the answer only. What does it mean? A first operand and same is the answer. A can be any value. So E is one value which is giving us the other in answer for all the possibilities. Then we say the identity element exists, and we say that the algebraic structure follows the identity property. Next is inverse. When we are given this set G, when for each element of G, means we are having A belonging to G, for that there exists an element A inverse in the group G itself, in the set G itself, such that A into A inverse is equal to A inverse into A is equal to E. So what we are getting in answer, that is the identity element. So if identity element exists, then we need to check for inverse element. Okay, so these are the three properties that must fulfilled to form the group. The algebraic structure will be called group if it is holding associativity property, identity property, and inverse property. And above all, if commutativity also holds, then we call the group is abelian. A group G is called abelian if AB is equal to BA for every AB belonging to G. That is, if G satisfies the commutative law. So, these are the requirements to form a group. Now, let us understand all the properties with the help of an example. So, here I am taking the set as UM. What is UM? UM is denotes the reduced residue system modulo M. What is that? UM. What is the operation? Operation will be multiplication modulo M. So, what the set will be? Set will be U12. It will have those values which can be remainder after dividing by 12. So, after dividing by 12, we can have 0, 1, 2 up to 12. Now, it is reduced residue. Reduced residue set means we will take those remainder possibilities for which the element and 12 are having only 1 in common, nothing else. It means they are relatively prime. So, if we consider the residues 1, 5, 7 and 11, these are not having anything other than 1 in common with 12. We have not taken here 4. Why not 4? Because 4 is having 2, which is and 2 is dividing 4 as well as 12. So, these are having a common factor 2. And what is a reduced residue system, in which we can have only we cannot have any common factor. So, let us understand with this example, it forms the group or not. So, what is my algebraic structure here? My algebraic structure is I am having this U12 set and my operation is multiplication modulo. So, if I consider this algebraic structure, what I need to check? First one is it associative in nature? Second is the identity property holds or not? The identity property. And third one is inverse element. Inverse element exists or not exists. Okay. So, to check these properties for this small set, we can have we can use the operation table or composition table. How the composition table is formed? In composition table, we take all the elements row wise and column wise. So, what I am having 1, 5, 7, 11 as the elements, and row wise column wise I am having again the same 1, 5, 7, 11. So, if I see here, what is my operation? Modulo multiplication. And what is M here? That is 12. So, 1 into 1 is 1, modulo 12, 1. 1, 5, modulo 12, 5. 7, 11. Okay. Same way 5. 25 modulo 12 is 1. 5, 7s are 35. Okay. So, modulo 12 is 11. 55 modulo is 7. 5 into 11, 55, modulo 12 is 7. Same way 7, 7 5s are 35, 7 7s are 49, 77. So, 5, 11, 11, 77, 1. So, this is the composition table. Now, we will check, is it associative, is it following the identity property, is inverse exists or not. Okay. So, first property is associative. It is associative in nature because modulo multiplication is associative in nature. So, first property holds. Second is identity element. Is there any element with which if we take the modulo 12 multiplication operation, is there any element with which if we take modulo 12 multiplication with any element, we get the same element in answer. So, let us check. If I take 1 here, 1 is an element When I am taking its multiplication modulo 12 with 1, I am getting 1 in answer, with 5, 5 in answer, with 7, 7 in answer, with 11, 11 in answer. It means we are having one identity element here. So 1 is the identity. So we have got one identity element such that when we multiply 1 with any of the elements, I am getting that particular element in the answer. So it means identity property is holding for this particular algebraic structure. Now the next property is inverse. When we take inverse, so what we need to check? We need to check for any element A, do we have another element B such that I am getting identity in answer. What is my identity in this particular example? That is 1. So I need to check for 1, is there any element for which I am getting identity 1 in answer? So when I see this, with 1 I am getting 1 the other element for which I am getting 1 in answer. For 5 I am getting 1 in answer for 5 on other side. For 7, 1, 7, 11. So what I am finding here, 1 is inverse of 1, 5 is inverse of 5, 7 is inverse of 7 and 11 is inverse of 11. So I found inverse element of each of the element of the set. The elements are 1, 5, 7, 11 and from here I am able to see that in this particular set, under this operation, all the elements are inverse of itself. So I got all the 3 properties true. So it is forming a group. Now we can also check, is it abelian or not? So when I go through the definition of abelian, so I need to check, is it commutative? So I am able to see here that the table is symmetric in nature. It means always AB is equal to BA. So it is an abelian group. So this way we can check it is a group or not. Now subgroup. What is a subgroup? Let H be a subset of group G, then H is called subgroup of G if H itself is a group under the operation of G. So I'm given this as the group. If I have been given another set H star, so it will form the subgroup of group G if it itself is a group. Okay, so how can we check? We can check the subset H is subgroup of G with following 3 conditions. If the 3 conditions are true, then it forms the subgroup. What is the first condition? The first condition is the identity element E must be present in the subset H. So I am having the group G and its subset H. So when I am having the subset H and I need to check it is subgroup or not, so first condition it must fulfill, that is the identity element must be present there. The second property is H is closed under the operation of G. What does it mean? It means if I am having AB belonging to H, then AB means A star B, that should also belong to H. When I am writing this simplified notation, it means I am referring to the operation A star B. Now, third, if H is closed under inverse, what does it mean? If A is present in H, its inverse must also be present in H. That is the closed under inverse. So it must fulfill 3 properties. The identity should be there, it must be closed under the operation, and it must be closed under the inverse. When we will have any group, it will always have 2 subgroups. Always it will have at least 2 subgroups. One is the singleton set containing its identity element, and one the group itself. These are called trivial subgroups. All other subgroups, then these 2 are called non-trivial subgroup. Okay, now let us understand with an example. So, let me take the group fourth root of unity 1 minus 1 iota minus iota. So, let me take the fourth root of unity with operation multiplication. So, my operation is multiplication. This is my group. So, let me take it as G. So, my G is 1 minus 1 iota minus iota, and let me take H as 1 and iota. Let me take it as H1, one subset, and I take another subset H2 as, let me take H2 as 1 and minus 1. So, what we need to check? We need to check H1 is subgroup or not, H2 is subgroup or not. So, I am taking the first one, that is H1. So, when I am taking H1, it is consisting of two elements, 1 and iota. So, now let us check, is it fulfilling all the conditions? So, let us take the first condition. The first condition says that identity element should be present here. So, what is multiplicative identity here? That is 1. So, 1 is present? Yes, 1 is present. So, first condition is fulfilled. If I note down here first condition, second condition and third condition. First, second and third condition. So, I am able to say that H1 fulfills the first condition. Okay. Now, second. What is second condition? Second condition says that it should be closed under the operation of G. What is the operation of G? Multiplication. So, I need to check the operation is closed for this particular subset or not. So, if I multiply this 1 into iota, iota is there. Okay. If I do 1 into 1, 1 is there. If I do iota into iota, I get iota square, which is minus 1. Minus 1 is not there. As minus 1 is not there, so what does it mean? It is not closed under the operation. So, I will leave here because it is not a subgroup. The second condition failed. It is not a subgroup. Now, we will check the next one. It is not a subgroup. Now, the next one, H2. If I consider H2, the first condition is the identity must be present there. What is identity? 1. So, is 1 present here? Yes. So, first condition fulfilled. Okay. Now, if I say second element, second condition, what is the second condition? It should be closed under operation. It means if I take any two elements from this set, the resultant must also be present there. So, when I am checking this, 1 into 1 is 1, which is present here, minus 1 into minus 1 is minus 1, which is present here, 1 into minus 1 is minus 1, which is present, minus 1 into 1 is minus 1, which is present. So, it means it is closed under the operation. So, because second condition is also true, now we will check for third also. What is the third condition? Inverse exists or not. So, what is the third condition? It should be closed under inverse. It means if A is present in H, then A inverse must also present in H. Must also be present in H. So, I am taking here in this particular one, what is inverse of 1? 1 into 1 is 1. The identity, it means 1 is inverse of itself. It means 1 is having its inverse here. Okay. Second is minus 1. What is inverse of minus 1? Inverse of minus 1 should be that element which will give 1 in answer. So, minus 1 into minus 1 if we do, we will get 1 in answer. It means minus 1 is inverse of itself. It means this element is also having inverse. Okay. So, inverse property is also true. In the previous case, we did not do that. We did not calculate because we did, second property was false. but now because second property was true, so I tried the third one also. So what I found, all the three conditions are true. It means it is a subgroup. It is forming a subgroup. So this is the definition of subgroup. Now coset. Let H is subgroup of G. Now we are not checking it is subgroup or not. We are taking an element. We are taking a group G, okay, and we are taking a subgroup H of this. So G is the group and H is the subgroup. Okay. Now what is coset? So let me take any element belonging to G. Then the set HA. What are the element of HA? Element of HA are H star A. Star is our operation. H into A means H star A. Such that H belongs to H is called a right coset of H. So we will have different coset. One right coset is corresponding to one element. Analogously means on the same pattern, if I take A into H, I will call it left coset. So let me take the same example. My group is, set is 1 minus 1 iota minus iota. My subgroup is 1 and minus 1. Okay. Now how to find the right cosets? So first right coset I will have corresponding to 1 because we need to take A belonging to G. So what are the elements of G? 1 minus 1 iota minus iota. So firstly I am taking the first element. So my one right coset is H1. What will be H1? It will be the right coset HA. It means H element is from H and A element is from G. That is 1 in this particular case. So we will have 1 into 1, 1. 1 into minus 1, minus 1. Okay. Now right coset, second one corresponding to minus 1. What will be this right coset? H minus 1. It will be 1 into minus 1, minus 1. Minus 1 into minus 1, 1. Now the third element, iota. Okay. Iota, 1 into iota, 1 into iota, iota, minus 1 into iota, minus iota. Same way next element is minus iota. So if I take corresponding to minus iota, it will be minus iota, comma, iota. So from here I got two similar coset and two different coset. Okay. So overall the right coset for this are 2, 1 minus 1 and iota minus iota. So these are the right cosets. This way we can calculate coset. Cosets are HA, where H is the subgroup and A is one element of G. Now a very important point we will discuss here. Let H be a subgroup of group G, then the right cosets HA form a partition of G. We have seen just seen on the last slide that when I calculated the right cosets for fourth root of unity, what was my fourth root of unity? Iota 1 minus 1 iota minus iota. What right cosets I got? I got right cosets as 1 minus 1 iota minus iota. So we can see from here that if I take intersection of these two, it will be phi. When I take union of these two, it will be G. So intersection will be phi and union will be G. It means these are forming the partitions. So it is a very important concept that let H be a subgroup of G, then the right cosets HA form the partition of G. So let us discuss this in general. Now, two things we need to prove that these are disjoint. Okay, and second thing is every element is present there in one of the right cosets. So we are talking about the cosets first. Okay, so since E, this is the condition for subgroup, since identity element is present in the subgroup, okay, and we know that A into E or E into A will be A only. This is the definition of identity element. Okay, so what does it mean? From here we can say A belongs to HA. Okay, so what does it mean? Take any element of the group G, it is present in one of its right coset. In which right coset it will be present? It will be present in the right coset which is generated from here, that is HA. Okay, so that is the first condition. What is the second condition? So it is giving us this condition true, means when we will take union of all, definitely all the elements will be present somewhere, so it will be equal to G. What is the second condition? Second condition we need to check is these are disjoint. It means if I take their intersection, it will give us phi. So let us prove it with the contradiction. Let me say HA and HB are not disjoint. So when these are not disjoint, it means there is something in common. So I have taken the element C as the common element between HA and HB, because this is common in both, it means it belongs to their intersection. So intersection is not phi, there is one element, I am calling that element C. Now because that common element is C and it is present in both HA as well as HB, it means C is equal to H1A for some particular H value, for some particular element of first HA, and C is equal to H2B for some element for coset HB. Okay, it is present in HA as well as in HB. So we have taken one element as H1 and H2 for which we are getting this particular element. As we know, both are from H only. Both are from H only. Okay, and C is equal to H1A and C is equal to H2B. So it means H1A is equal to H2B. Because they are belonging to H, it means they are closed under inverse as well as operation. So simply we can take A is equal to H1 inverse H2B. Why? Because inverse is also present in the set. It is closed under operation as well as closed under inverse. Okay, so A value we have calculated with this assumption. Now I need to prove that if there is something in common, it means both are same, because if both are not same, it means it is not a contradiction. Okay, so I am taking one element X which belongs to HA. As it belongs to HA, so I have taken X is equal to H3A. A value I am putting from here. So what I will get? H3 into that A value. What is A value? H1 inverse H2B, where H3 also belongs to H. Because H3 is also belonging to H and H is the subgroup. Okay, what does it mean? It means the complete element is also belonging to H. Okay, it means X belongs to HB. So when I have taken X belongs to HA, I got X belongs to HB. Okay, so what does it mean? HA is a subset of HB. Reverse can also be done on the same pattern. So we can show from here that when HA and HB are not disjoint, it means they are same. Okay, so if these are not disjoint, these are same, otherwise these are disjoint. So what we have shown? We have shown that the right coset HA form partition of G. Now we will use this in Lagrange's theorem. Another thing we should know, the very important result, let H be a finite subgroup of G, then H and HA H, the subgroup, and HA, it's any coset, have the same number of elements. We can prove this easily. Let H is H1, H2, Hk. It is having k elements. So what will be HA? HA will be H1A, H2A, Hka. Okay, so finite subgroup we have taken, so finite coset will be there, HA will be finite one. Now, if we say that both are not having same order, what does it mean? It means there are two elements common here. Common means same, that's why we are saying that it is having k elements, but that one is not having k elements. So let me take HIA is equal to HJA. But now A is having its inverse. So because A is having inverse, so we can say H1I is equal to Hj using cancellation law. Cancellation law hold because there is inverse element for these. So what does it mean? Hi is equal to Hj, but here no Hi is equal to Hj. It means all these elements are distinct. So it can be said directly that H and Ha have the same number of elements. So these two will form the base for Lagrange's theorem. What is Lagrange's theorem? Let H be a subgroup of a finite group G, then the order of H divides the order of G. So we will use the two properties that we have discussed on last two slides. Okay, so consider H is having R elements and there are S right coset. So what are right coset? S in number, it means HA1, HA2, HAS, HA1, HA2, HAS. These are the right cosets. So as we are having S right coset and each coset has elements same as subgroup as we discussed on the last slide, what does it mean? The total partition is having R into S element. The coset partition G and each coset has R elements, therefore G has R into S elements and R into S is divisible by R. So what does it mean? The order of H divides the order of G. So we can check from previous example also. What example we have taken? Fourth root of unity, 1 minus 1 iota minus iota. What was my subgroup? 1 and minus 1. So what was order of this group? That is 4. What is that order of this subgroup? That is 2. Order of this was 2. What is order of a group? The number of elements in the set. Okay, so we can easily see that 4 is divisible by 2. So this is Lagrange's theorem. Let H be a subgroup of finite group G, then the order of H always divides the order of G. Now normal subgroup. Now again we are given a subgroup and a group G. A subgroup H of group G is normal subgroup if A inverse HA is subset of H for every A belonging to G, or we can say AH is equal to HA. What does it mean? It means right and left cosets coincide. AH and HA, this is left coset, this is right coset. When left coset and right coset coincides, it means it is a normal subgroup. We can take the same example. So what is my example here? That is, I am having the group 1 minus 1 iota minus iota. Okay, my subgroup is 1 minus 1. This is my G, this is my H. If I calculate HI, one right coset, so it will be I into 1 into I, 1 into I, minus 1 into I, minus 1. Okay, right coset. Now let me calculate left coset. This is my right coset, that is my left coset. What is my left coset? I into H. So if I do I into 1, again I am having multiplication I into minus 1, minus I. So here I can see that HI is equal to IH. So my subgroup is normal subgroup. When left cosets and right coset coincide, then it is normal subgroup. Every subgroup of an abelian group is normal. This group was abelian group. Okay, so its subgroups are normal subgroup. So in this particular video, we started with groups, and with an example we understood how to check the properties for group. After that we studied the definition of subgroup. When a subset of G forms subgroup, what are coset, what are normal subgroup, and very important Lagrange's theorem. Thank you. Jai Hind.